So good morning, good afternoon, good evening, wherever you're joining us from today for the Meeting Minds Global 2021 Physics booth. I'm delighted that you're joining us. My name is Val Crowder, and I am the Alumni Relations Officer for the Department of Physics. And today I'm delighted that two of our senior members of the particle physics sub-department are joining us to talk to you about the latest findings in particle physics. So it's my pleasure to introduce Professor Malcolm John, who's a particle physicist and one of the senior academics leading Oxford's work in physics on the heavy quarks, specifically charm and beauty quarks. For over 20 years, his group has been involved in the conception, design, commissioning, and operation of the LHCb detector, which studies such physics as at the LHC at CERN.
Hello.
Dr. Sam Henry, pardon?
Hello.
Welcome. And Dr. Sam Henry is a Detector Development Scientist and has worked on many experiments from the search for dark matter to an attempt to measure the shape of the neutron. He's actively promoting public engagement with research. His most noteworthy achievement in the university is winning the MPLS award for his My Little Pony fan fiction. I recommend everyone following that, and I will share the links on the text box and the question box later. He's also worked on the Muon G-2 experiment, which he will talk about today. So on that note, welcome everyone. Let me admit more people. And on that note, Sam, the floor is yours.
Okay, thanks very much, Val. Right, I will try to share my slides. Right, so if this is working, then yeah, you should be able to see me and pictures of the Muon G-2 experiment. So I'm going to be talking about some exciting results in particle physics, which just came out last week, which was the release of the first data from the Fermilab Muon G-2 experiment. So I'll explain what G-2 is and about how we measure it and why it's so important. And maybe a brief bit about what we've actually done on this experiment here in Oxford. Okay, but maybe to begin with, I should just say a bit about, well, what is actually the muon. So the muon is, in some ways, it's one of our favorite particles. It's sometimes described as a heavy version of the electron. It's a fundamental particle. It's got a mass about 200 times that of the electron. And it's a nice, easy particle to study because it's got a lifetime which is a whopping 2 microseconds long. So we can produce lots of muons. We can study them in great detail. But it's also more exotic than the electrons. So that means that by studying it, we can get some hints of new physics. And that's why it's one of our favorite particles to study. So it's not as difficult to deal with as things like the Higgs boson, which decay before you even see them. But it's more interesting than just basic things like protons and electrons. So next thing is, what is the G-2 factor? And there's various ways I could answer that. I could just tell you, well, it's what you get if you subtract 2 from the G factor. I could tell you that G-2 is 116592061. But I guess what you're really wondering is, well, what is the actual significance of this number? And the G-2 factor is it's the muon anomalous magnetic dipole moment. So the G factor is it's a sort of normalized magnetic dipole moment. It's a measure, if you like, of how magnetic the muon is, of how it interacts with the magnetic field. And the great thing about the G factor is it's something that we can both calculate to a very high precision, and we can also measure it to a very high precision. So we're now at the sub-parts per billion level in our precision of both. And there seems to be a subtle difference between the experimental value and the theory. This could be a hint of some exciting new physics that's going to come along. Okay, so just to begin with, I want to give a sort of historical introduction to the theory. So the question here is, why is G not 2? So the history here is that if you look at the muon magnetic dipole moment using classical physics, then you would expect that the G factor is exactly 1. But then when we had quantum mechanics arrive and the Dirac equation, this then predicted that G is equal to 2. So that was an exciting development. But it was then shown in more precise experimental measurements that G is actually not quite equal to 2, which was initially not understood. But then the theory of quantum electrodynamics arrived, and this then tells us that all particles are surrounded by a virtual cloud of virtual particles, of particle-antiparticle pairs that keep appearing and disappearing, and this will shift the value away from 2. So the first refinement of this theory was when it was shown, well, if the muon interacting with a photon, then if it first radiates a virtual photon that's then reabsorbed, then this will then shift the G value to about 2.00232. And you can go on doing this calculation by considering more and more virtual particles, and you end up drawing more and more of these Feynman diagrams with extra photons, and then the extra photons can produce particle-antiparticle pairs. And then it becomes an incredibly complicated calculation. So when you get to 5th order, you've got over 12,000 Feynman diagrams to consider. And you have to consider the contributions of all of the theories, all of the particles in the standard model of particle physics. So it's not just electromagnetism, because the virtual photons can then radiate a quark-antiquark pair. And so there's an awful lot of calculation to do. But this also means that the value of the G factor is sensitive to every particle in the standard model. So it will come into it due to these vertical particles that are being produced. And this is why it's so interesting, because by taking a precise measurement of this one number, this measurement of how the muon interacts with the magnetic field, we can indirectly study all sorts of particles, and this might give us a hint of some new particles that haven't yet been discovered. So that's how the calculation's done. So the next question is, well, how do we actually measure the G factor? And we do this by measuring the muon's spin precession frequency inside a magnetic field. So you can do this with an analogy to a gyroscope. When you have a gyroscope which is spinning around, then its axis of spin, if you tilt it over, the axis will then precess around and around about the vertical direction. And for a gyroscope, the spin precession frequency will depend on its dimensions and due to the acceleration due to gravity. But when you have a particle with a magnetic dipole moment in a magnetic field, it will also precess around. And in this case, the spin precession frequency will depend on its magnetic dipole moment and also on the magnetic field. So if you can take a precise measurement of the magnetic field and of the spin precession frequency of the muon, then this gives you a way to determine the muon magnetic dipole moment to a high precision. And because what we're measuring here is a frequency, so it's just counting the number of times something goes up and down, then it means that we can do it to a high precision. But of course, there's all sorts of things that can complicate the measurement, so we have to take into account all sorts of extra experimental uncertainties. So let's go into a bit more detail about how you actually do this experiment. So the first step is you want to produce your muons. Now, as I said, muons are a nice particle to work with. They're easy to produce. You just take a proton beam, you wham it into a target, and this will then produce all sorts of stuff, including lots of pions, and the pions will then decay to the muons. And then once you've got your muons, you will then inject them into a storage ring. So although the muons will live about 2 microseconds, if you have them moving at close to the speed of light, then due to time dilation, then it will be a lot longer. But they're a charged particle, so to store it, you have to have it inside a storage ring. And so as the muons are then moving around the storage ring, the axis of the spin will then be precessing about this direction. And this is what we want to measure. So we don't actually measure the precession frequency of the muons directly. We measure it from the positrons that the muons then decay to. So we have lots of particle detectors on the inside of the ring which are detecting these positrons, and we're looking at how the count rate goes up and down and the frequency of which that happens. But the spin precession frequency is only half of the measurements. The other half is measuring the magnetic field. And so that has to be done with an awful lot of magnetometers. So there are proton magnetometers all the way around this ring. So that's just the diagram. Now thinking about a real experiment. So the history of this measurement was that back 20 years ago, the Brookhaven National Laboratory did a measurement of G-2, and so this is a picture of their ring, which is 14 meters across. And this caused a lot of excitement at the time because this was the first measurement which seemed to differ from the standard model prediction. So it differed by 3.6 sigma, 3.6 standard deviations. And so that experiment over the years has been one of the most cited results in particle physics, because it seemed to be a hint of something new beyond the standard model. So there was a lot of interest in trying to repeat this measurement to a higher precision in order to see if it is indeed a real effect. And so they drew up a plan to do this, which was to move the experiment from the Brookhaven laboratory over to the Fermilab laboratory and repeat the measurement. So the Fermilab laboratory is the biggest accelerator laboratory in America. So until the Large Hadron Collider started up at CERN, this was the high energy frontier. They had the Tevatron accelerator at Fermilab, which was colliding protons and antiprotons, and so that was where many particles were discovered in particle physics, where the top quark was discovered, where the bottom quark was discovered. So this is a big center. And then after the focus of the high energy frontier, if you like, moved over to CERN and the Large Hadron Collider, then Fermilab were keen to keep going with their research program. So one of the things they've done is to move into muon physics and to produce a very intense muon beam, which could be used for the G-2 experiment and also for other projects. So it's also producing a neutrino beam, which is then used for other experiments. Just an aside, Fermilab is also the home to a herd of bison. So you can so if you look at your website, you can get plenty of cute pictures of the bison calves that arrive every year. Okay, so the idea was that because Fermilab had this more intense muon source, that this could allow the G-2 collaboration to improve the precision of their measurements. But to do this, then they had to ship their experiment from New York over to Chicago. So in the Brookhaven laboratory, the experiment was built with this 40-meter diameter magnet. And while a lot of it could be dismantled and just trucked across the country, the core component of it, this 40-meter diameter superconducting magnet, couldn't be broken. So this then had to be shipped. And indeed, this was the subject of a lot of studies. But it was found it was, although the cost of shipping it was some $2 million, that was still a factor of 10 cheaper than actually rebuilding the thing. So so just to show some photos of this big move that happened in 2013. So this was dismantling the magnet at the Brookhaven laboratory, and although the main core components were then just put into trucks, but you have this core superconducting ring. This was then moved out of the Brookhaven laboratory in the middle of the night when they could close down the roads. And because the ring, the requirement was that the ring couldn't be distorted by more than a few millimeters, so it had to be mounted in this very secure supports to keep it in one piece. And this was then loaded onto a barge, and that was then shipped down the east coast of America and then across the Gulf of Mexico. And every step along the way was of course logged on social media. And at this point, many members of the collaboration were rather nervous because they were aware that, well, this is probably the biggest risk in the whole enterprise. That if something goes wrong, if it falls off the barge or something, then that would end the whole experiment. So there's some pictures going past some big landmarks in the middle of America. And then eventually it reached Illinois, and it was then offloaded from the barge and then moved onto the freeway and into Fermilab. So this last stage was the most complicated step, where it only just managed to fit through the toll booths. But then eventually the magnets then arrived on the Fermilab site, and there was a huge party to which all members of the local community were then invited. And the local brewery produced a new beer just to celebrate the occasion. So that was a big excitement, and once that hurdle was overcome, then well, initially the magnet was just sitting in the parking lot at Fermilab for some months, but they then started to reassemble the whole experiment once all the other components had arrived. And producing this experiment is a real big challenge because the 40-meter cross ring, the muons are circulating around it, but the magnetic field inside it has to be very precisely controlled. So it has to have a uniformity of less than a 1 part per million precision. And so that meant that there had to be a lot of adjustments done. There was a robotic probe made that would run all the way around the ring and measure the magnetic field. And then a challenge was it was mapped, and then it would be noted that the magnetic field wasn't perfectly uniform. So they'd then be adjusting the current in some coils or changing a spacing of some magnets in order to adjust it, and then remeasuring it. And so this kept a lot of students busy for a summer, just producing the reassembling the magnetic and adjusting the magnetic ring and adjusting the magnetic field. So then, so I think we've got another picture of the full ring here. So so this was built in what was known as the Fermilab Muon campus, which is then a new part of it. And the intention is that muon physics will be an exciting part of their new program. Okay, so I just sort of say a short bit on how Oxford was involved. So Oxford are no longer members of the collaboration, unfortunately, but there were three of us, myself and Farouk Asfar and Babak Abi, who were involved with the experiments for a few years, and so we're authors on the paper that's just come out. So one of the things that we wanted to do is we wanted to build a helium-3 calibration magnetometer. So magnetic field measurements are at the heart of this experiment, and this is done with hundreds of proton magnetometers all the way around the ring, but they all have to be calibrated against one standard. And so the collaboration had a standard probe using a water sample that was used, but they wanted to cross-check it against a new standard using helium-3. And so this was something which Oxford did a lot of the preliminary research on how you can do this. So these magnetometer probes are all NMR magnetometers, so they're also measuring a spin precession frequency, but of the proton, or in our case the helium-3 nucleus. And then by taking precise measurements of this, you can measure the magnetic field. A helium-3 can, in theory, give you a much better calibration, but the challenge is that in order to produce lots of polarized helium-3, you have to optically pump it, which means you need to have a laser system to do it. So we did a lot of initial research in setting up a laser laboratory and building a prototype probe and doing this. Unfortunately, we weren't able to complete this project due to lack of resources and management issues. So in the end, we had to hand over this project to the University of Michigan, but we did a lot of the initial research on this. So then, after leaving the collaboration and leaving it over to our colleagues in Michigan and elsewhere, then at that point we were then. For a while, of course, we didn't really know what was happening. We were no longer getting emails, but we knew the measurement must be taking place. And so then we were really excited when we got the news that the first results were then coming out this year. So this the analysis of this data was done as a blind analysis. So this is because people were well aware of just how important this result was, and there was always a temptation when you're analysing the data and you think you know what the value is, that you might just somehow fudge your analysis to give the result you want. So to avoid that, the data was blinded. The way this was done is that, of course, we're measuring frequencies, and every frequency has to be is done by comparing the rate of something to a standard clock, and so the clock which would have been providing the signal to the apparatus was given a slight offset, but the value of this offset was kept secret until the analysis was complete. So there was a big unblinding ceremony just a few weeks ago to which we were invited, where they then typed in this offset into the spreadsheet and then could suddenly see for the first time that the result was indeed what they're expecting. So I'll just show a few pictures of some of the data. So this has come from the latest paper, which is available on open access. So if you want to get the full technical details, you can have a look at this. So the data is measuring two things. It's measuring the muon spin precession frequency and also the magnetic field. So I've just got one picture on each. So this is the muon spin precession. And what this plot is showing is all of these wiggling lines are the counts of the muons, or rather the counts of the positrons that the muons decay into against time. And then this line has been wrapped around about 8 times. So as the number of positrons keeps decaying, but the number is oscillating up and down at the spin precession frequency. So that's the raw data, and then you have to measure this frequency very precisely, which is done using various different analysis with Fourier transforms, just fitting a function to this, and then that gives the muon spin precession frequency. The other exciting thing is then the magnetic field. So this is done by, as I said, with hundreds of probes all around to then map the field to a subparts per million precision. So this graph is just giving the average magnetic field of the cross section of the beam pipe. And as with all of these precision measurement experiments, they have to keep very close track of all of the uncertainties on of these quantities. So if you look at the papers, you'll find there's table after table of what is the uncertainty on every measurement and how this then factors into the uncertainty on the final result. So when we put it all together, then this is then the results, which is then showing that yep, the new value measured at Furby Labs, so that's the red line on this plot, was indeed consistent with the previous measurements of the Brookhaven experiment, and it now seems to be 4.2 sigma away from the standard model prediction. So this was, when this result came out, this was of course a big relief for everyone who had worked on the earlier Brookhaven experiments, because of course until this point there was always this question, well, had they just screwed up that measurement? And so that was the big relief. And it also would seem from this that yes, this deviation, it isn't just a statistical fluke. It looks like it is a real thing, although it's still less than the 5 sigma difference, which is the generally accepted standard within particle physics to announce a discovery. Now, of course, what everyone now wants to know is, well, what does this mean? And of course, there's all sorts of particle theorists who are coming out with theories beyond the standard model, which could then try to explain this. And yeah, it could be due to some new particles that not yet discovered. So this is so there is indeed been a lot of papers by theorists coming out. But of course, this isn't actually a measurement which is giving us a very clear direction of what direction the theory needs to go in. It's just telling us that there's something which doesn't fit the standard model. So that's why we still need the results from the Large Hadron Collider and other experiments to give us more information. And of course, the other interest is, well, is the theoretical calculation correct? And indeed, this was the subject of another paper which been released recently, which is attempting to redo the calculation using the theory of lattice QCD. And this actually suggested that actually there wasn't a discrepancy. Now, this new calculation is not in line with the previous calculations. So of course, there's a lot of so it's not yet widely accepted. But, you know, and if it is wrong, then of course, then the question is why the previous calculations were giving a value which differs from the experimental value. So there's clearly something which isn't right. And we need a lot more research, both on the theoretical side and the experimental side, to try and figure out what's going on. Okay, anyway, I think I've been chatting a lot. So are there any questions at this point? So if I open up the chat, or Val, are there any you've spotted?
So far, let me go to the top. We have Ian sharing that he's been, he did his DPhil on the LHCb experiment from 2002 and 2006. So that's great to have you here. And let me see, I have a question from Ian. I understand there is an alternative theoretical work by BMW group, which gave the value of G-2 closer to the experimental value than the theory initiative value. This has been widely reported in the scientific media. What is your view on BMW data?
Yes, indeed. Yes, this is the calculation using the lattice QCD. So it is indeed very interesting. So the way the calculation is done is one of the big uncertainties in the calculation of the Muon G-2 factor is what's called the hadronic vacuum polarization term. So this is when, if you have a virtual photon which is radiated by the muon that then produces quark-antiquark pair, so that's then producing hadronic particles, then so this is where the theory of quantum chromodynamics comes into it. So this is one of the biggest uncertainties, because the calculations involving the quantum electrodynamics can be done much more precisely. But with QCD, it's a much more messy theory. There's a lot more uncertainty on these values. And so the way these calculations had generally been done in the past is by using experimental data from electron-positron colliders who have measured the precise cross-section of processes where quarks and positrons are annihilating, produce quarks. And then these experimental measurements can be used in the calculation. So this alternative approach of lattice QCD is actually calculating it using lots of supercomputers. Now that theory is far too complicated for me to understand. I'm just an instrumental scientist, so I really can't say whether or not it's correct or not. But it's certainly very interesting because it seems to be giving a value, which is, yes, in line with the measured value of G-2, but not the previous calculations. So it will also seem it's not matching these measurements that have been done in other experiments. So exactly what's going on, yes, we don't yet know, and yeah, so we're all certainly looking at it with lots of interest, but yes, it's not yet obvious which one is right.
Thanks, Sam. So we'll take one more question, and then I'll ask everyone please to wait till the end of Professor John's talk, and then we'll take all the Q&As later. But I see Daniela with her hand up. So if you'd like to post your question now, that'll be great. You are welcome to come on camera if you like. Otherwise, just share your question with us. Thank you.
Sorry, raised my hand by mistake, but a great talk, and I'm looking forward to hearing everything of the CERN. Sorry.
Not a problem. Okay, on that note, then we welcome Professor Malcolm John. And then, like I said, please keep asking your questions on the chat box or wait till the end of his talk, and we'll have a longer Q&A session. Thank you.
Okay, thanks very much. Yeah, maybe I can air my opinion on the BMW result. Yeah, I mean, I can't speak authoritatively about this, but it is. I mean, one should give a certain amount of respect to the G-2 theory initiative, which has been going on for many years in a coordinated way. And although, of course, they should consider this this new result using lattice QCD, let's not throw the baby out with the bathwater in pouring some skepticism in both directions. All right, I have got some slides which I'm going to put up behind me. Hopefully this comes through reasonably well. Oh dear, where are they? Hold on.
Not a problem. Take your time, Malcolm. Thank you, everyone. I'll share in the meantime. Thank you again, everyone, for joining us. It's great to see so many of you, so many names that we know, and hopefully we have a lot of people who are not physicists here in the audience today. Are you back in, Malcolm?
Alrighty. So I think I'm here. Okie doke. So yeah. So what I'm going to do is I'm going to talk about a slightly different result that's from LHCb, although there is some connection that can be made, which I shall speak about at the end. So LHCb, the LHCb experiment. So it's an experiment at the LHC, so it's at CERN, and here on your screen you will see that the picture of the LHCb experiment with some sort of scale given by my colleague Gloria, who's standing there on the green scaffolding. The actual experiment is at the back of the hall there, running left to right across the picture. The bluish object standing behind Gloria is the LHCb dipole magnet, of which separates charged particles to the left and to the right, and we use this in order to do our main physics program, which is studying the differences between matter and antimatter through the production of principally B mesons at the LHC. So this gives you an idea of scale. So it's underground, 100 meters underground, next to Geneva Airport. Now let's focus right to the very heart of that experiment. And this is an event display of the production of a BS meson. Okay, so what is a BS meson? A BS meson is a bound state of a B quark and a S quark, or a strange quark, and these are produced copiously at the LHC. I calculated that there are something like 100 billion BS have been produced within the LHCb acceptance from around 10 to the 15 PP collisions that have occurred over the last decade. And of those BS mesons that are produced, they will fly a little bit. And in this particular example on the screen, it's flown 17 millimeters before decaying into a final state. And this final state here is that I've highlighted is where it's decayed just to a pair of muons. The faint structure that you can see around the principal green tracks is the detector material that is imaged there. But that's it, this huge experiment just to understand what is going on in a very short distance right at the heart of the experiment. And the decays I'm going to talk about all involve muons in some way today, or the measurements. So this BS meson flies 17 millimeters and decays to a pair of muons here. So if we draw a Feynman diagram, so this Feynman diagram will encompass the knowledge of the what's going on at that very short distance of the point at decay, and we can see that in this Feynman diagram how the B and the S quark that are contained within the BS meson can decay to a pair of muons. And this diagram you see here is actually relatively complicated. It has a triangle structure, and it has several intermediate particles, two W's and a Z. And it's the fact that this diagram has all this complication, which leads to this decay being particularly rare. The simpler diagrams always will have a higher probability of occurring. These more complicated diagrams are rarer. And so within the standard model, the calculation of the branching fraction, how often this decay occurs, is a really small number, right? And the small number is 3.66 plus or minus 0.14 times 10 to the minus 9. So now you sort of understand why we have to produce 110 billion BS mesons, is because we're looking for a sample of something which occurs 3 in 1 billion times. So if you want to study this in some sort of precision, then yeah, we need a lot of them. And so here's a peak of data. Now in these sort of plots, a peak means that there is an excess of events at a particular invariant mass of 2 muons. So this is where you've taken the 2 muons which have been successfully measured in the detector, and their momentum have been measured. You've added together their momentum, or more precisely their 4 momentum, and calculated what their mass is. And if these 2 muons have indeed come from a BS meson, you'll get a peak, you get a mass peak, which is what we see here. And then it is fitted really to show what we're talking about. So the red fit there shows the BS peak. And properly normalized, one then makes a measurement to how often that has occurred, and what is being measured by LHCb with the latest data is 3.1 plus or minus 0.5 times 10 to the minus 9. So it is again one of these games of comparing the theoretical prediction with the experimental measurement. And there is, I mean, in this particular example, the discrepancy is not so large, but it is slightly discrepant, let's say. However, if we roll in data not only from LHCb, but also from the other experiments at the LHC, so Atlas, which Oxford is also involved with, and CMS, its main competitor, then the significance of the difference grows a little. So overall, if I add together all these results and I compare the difference between the experimental results, which is shown here in blue, compared to a normalized value of the theoretical expectation, which is shown in yellow, there starts to be a difference. And this difference here is not quite 2 sigma, okay? But a little bit interesting, right? But that's not the main thing I want to talk about today. But it gives you an introduction to the style of physics we do. I've shown you the Feynman diagram already for BS to mu mu decays, okay? So this is the BS to mu mu decay at the top, and at the bottom I put another Feynman diagram. Now, this is different decay. This is a B plus meson, which is decaying to a kaon with the emission of a pair of leptons, okay? So the curly L plus curly L minus at the bottom of the screen there is represents the leptons. In particular, what leptons we're talking about here is either a electron or a muon. But if you look at the quark transition here, it also involves the transitions of between a B and an S going to a pair of leptons, which is ultimately the same quark level transition as in the BS to mu mu diagram at the top, which is a B going to an S connecting to a pair of muons. So there is a deep connection here between these two different styles of analysis, even though they're otherwise completely separate particle physics analyses carried out at LHCb. So let's look at this second decay here. So this is a 3-track final state, a kaon plus 2 leptons. And this time we're going to compare the rate with electrons to the rate with muons. So let me cut to the chase before I go through the details of the result. Let me tell you where we're going with this, right? The latest result from LHCb, which was released about a month ago, says that the ratio of this RK between that decay involving muons and that B plus decay involving electrons is significantly 3 sigma away from 1. Now, it is an absolute tenet of the standard model that the behavior of the connection of the weak force and the weak force and the electromagnetic force to electrons and muons is the same. The only difference comes down to their mass, but that's a very, very small correction. So we really expect the ratio in the rate of the B plus decay going to a kaon and electrons or muons to be the same, i.e. the ratio of them to be 1. And this result has been growing in significance over the last few years. There was a couple of measurements by Bell and the Barbar experiments, which are shown there, rather imprecise in the early 2000s. But then LHCb in first 2015, then 2017, and now in 2021 have produced increasingly precise results, which are marching away from this quantity being 1. Let me give you a little bit of experimental detail. So here are some mass peaks. So again, just how we saw the BS to mu mu mass peak, which was only a little mass peak. Here are another pair of mass peaks for the final state we're talking about now, which is a B plus going to a K plus and radiating off either a pair of muons or a pair of electrons. Now we look at this and you can see by eye that, well, hold on, the peak that involves muons at the top of the page is already pretty large and seems much larger than the one involving electrons at the bottom of the page. This is simply a reconstruction effect. It's harder to reconstruct electrons at the LHC because there's considerably more background for electrons. So this is actually completely normal, and it's just an experimental effect. We have to do a couple of clever tricks in order to correct for this, and the way we correct for it is by doing a double ratio. What do I mean by that? Is that we compare the decays which we're most interested in, this K mu mu and K E E decays, which I re-show on the left-hand side, and we take each one of them, we divide by a very similar decay, but where that mu or EE pair has been produced going through a J-psi. And the J-psi is another meson, but it is very well established as being very standard model-like. But the final state is the same. The fact that it's passed through a J-psi resonance very briefly has very little effect on the detector response. So you're able to factor out the detector response by doing this clever double ratio. So it makes this RK measurement really very robust to experimental effects. And these have, of course, been checked in some detail by the analysis team. So you expect the RK is equal to 1, and we're seeing 0.85 plus or minus 0.04. So it's edging above 3 sigma away from expectation. And from an experimental point of view, it's pretty hard to see how this RK ratio could be wrong from an experimental point of view. And the theory is absolutely unquestioningly, there's no lattice QCD guys out there who are going to mess this up. It really is an absolute standard bearer statement from the standard model to say that this RK should be 1, that electrons and muons feel the electromagnetic and weak force equally. So, my slides. So you could ask, okay, so it's not the number is less than 1. So does that mean we have too few muons or too many electrons? Well, in a separate result, one can measure the cross-section of the muon and electron processes, and what we see that, so here's a little bit, a graph that's a little complicated. I'm measuring against Q squared, which is the amount of form momentum squared that's passing to the lepton pairs. But the key point I want you to take out of this is that the red is the expectation from the theory, the blue is the electron result, and you see it's low, but it's completely compatible with the expectation from the theory in that first bin. The analysis is not done in the higher bin. And it is the muons which are deficit. So it appears, the indication is that there is a difference between muons and electrons in the LHCb data, and that the problem is with the muons, not the electrons. So here I show my BS to mu result, which was the LHCb result plus the Atlas and CMS numbers, and it's edging towards 2 sigma. And then once again, this is a decay which is sensitive to B quarks going to S quarks and emitting muons. And then at the top of the page, it's the RK result that I've just been talking about, where you have again B S quarks going to muons or electrons, with the problem appearing to be with the muons. But these results aren't alone. Here is a whole suite of LHCb results, all rather similar in nature. So all the things which have got capital R's at the top of the list, they're all this sort of ratio of muons to electrons, the same star measurements, but with slightly different decays. We study in not only charged B mesons, but neutral B mesons, BS mesons, similar sort of measurements, and they're all showing some discrepancy. There are angular measurements. There are measurements of rare decays like the BS to mu. And then at the very bottom, what is added is the muon G-2 result, which is nothing to do with LHCb at all. And I'm just tagging it on there to show that that is the most standout result still globally at over 4 sigma away from the standard model. But of course, the question is there a connection here? And at this point, this is really sort of like personal speculation. But it's clear that these are all to do with muons in some way. So the bottom of the 2 Feynman diagrams I'm now showing is the quark level transition for the RK result, where we have a B quark going to an S quark, emitting a pair of leptons. And speculatively, one is putting here a connection between them, something which I'm labeling LQ. All right. And what is LQ? Well, LQ is a speculative theoretical construct called leptoquark. The leptoquark has got the unique and special property, if it were to be shown to exist, that it connects between quarks and leptons. Direct connection between quarks and leptons. Okay. Now, that could explain this RK result. It potentially could be a new current of nature that is being detected in that process, and it's interfering with the standard model process. And the question is can you put a leptoquark potentially into the G-2 result? And this is also possible in principle. So that's on the top diagram. So in the G-2 scenario with the leptoquark, you have a muon, which is connecting to a B or S quark. So the B quark or the S quark are now internal to the Feynman diagram, and a loop of leptoquark have been produced for a very short time. And in that short time, the muon has interacted with the magnetic field, which is making it process. Now, I'm of course not advocating this particular model or saying that this is in any way the truth, but it highlights the point that there is some possibilities of connections between the intriguing divergences from expectation, both in the new Fermilab results and results coming out of the LHC. And yeah, at that point, I think I'll leave it.
Very much, Malcolm. So I will start asking you both a couple of questions that were being posted on the chat box. And again, for all the latecomers, welcome. And if you like to pose any questions, you can either write them on the chat box or use the icon at the bottom of your screen that says reactions. You can raise your hand and we can let you in live on the talk. So my first question is from Ronald. Ronald says, as a non-scientist, I am interested in the long-term practical implications of this fundamental research. I have had the privilege of visiting a synchrotron in Saskatoon, and I have seen some of the benefits for medical research and treatment. What are your biggest hopes for the real-world implications of this work?
So, I have to say is that the direct use of the discovery of a new force of nature will not turn up in consumer electronics anytime soon. Honestly, however, one shouldn't look at it like that. Is first of all, it's I believe what we do speaks for itself in terms of for intellectual curiosity, to understand how the universe functions at the most basic level does inspire a lot of people, and I think a lot of people find a value in that. And one should say this is just not some minor curiosity. If it turned out that this was a fifth force of nature, it is certainly the work of will be a work for many years for people trying to put it in a coherent model to explain other oddities that we know of in science. Big ones being the dark matter. Dark matter is seen in the behavior of galaxies, but the particle which is causing that extra gravitational effect of dark matter, we have no idea what that particle is. Don't know that a leptoquark will give the answer to that, but it might do. Might give some indications to theorists to look and think about things in a different way. And the other big question is the acceleration of the universe, dark energy. It seems pretty convincing that the universe is accelerating in its expansion, which our our simple understanding of gravity really can't explain. Gravity gravitates. What's the universe doing accelerating? And there, potentially, models involving leptoquarks might have some opinion on that. But I say it's a long way from this being proven. But nevertheless, I believe that is food for intellectual minds to inspire people well into the future. If you're not satisfied with that answer, I would talk about the service to no, the service is the wrong word, but the technology improvements which do come out of particle physics do have real world applications, and there are many of them. I mean, you speak of a synchrotron. Synchrotrons exist in medical facilities, and it's not just the initial ideas, but the technological improvements in magnets and in accelerators that is made in particle physics will have practical applications in medicine and other areas. Yeah, so that's somehow how I would answer that question.
Thank you. Another question from Matt. What are the leading ideas for the theoretical experiment? I beg your pardon. What are the leading ideas for the theoretical and experimental discrepancy? Either the speakers?
Well, it's new. It's new, and my personal little illustration, which I've just given here with the leptoquark, I think is very nice, because you can, with a few lines on a piece of paper there, you can see how two very different results, one which is talking about a muon rotating and the result of a rare decay at LHCb could be explained in a sort of coherent way with the construct of a leptoquark. However, I should say that the leptoquark is that leptoquarks not a new idea. Leptoquarks have been looked at for generations now, but mainly involving interactions of electrons with the structure of protons. And the structure of protons is dominated by the lowest mass quarks, U quarks and D quarks, in deep inelastic scattering experiments that Sam briefly touched upon. And so what's intriguing about this is it the case that electrons behave perfectly normally and do not connect to leptoquarks? And maybe muons do. And that's an interesting idea which we will try and chase down.
Thank you. So next question from Diego. Does muon particles may affect photon particles when we have a light, in brackets, laser refraction?
I guess maybe I can say that because maybe that follows what I was saying about the lasers and our machometry. I mean, I think muons will interact with photons in just as electrons will do as their charged particles. So yes, in some ways, whether they're interacting with it due to through a magnetic field or through laser light or through anything else, yes, they will. But the lasers that we were using on our machometry, that wasn't actually coming anywhere near the muons. We were just using the lasers to set up our sample of helium-3 gas in such a way that we could measure the magnetic field in that, and then we were using that to cross-calibrate another magnetometer that would then be used in the experiment with the muons. So I think yes, the answer is yes. Muons do, of course, interact with photons just as any other charged particles do. But we're not actually using lasers to directly probe the muons in our experiments. But other experiments do use lasers.
Thank you. And this other question from Daniel might follow on that. So the question is, how are the muon pairs detected at LHCb?
Yeah, muons are, I would say, for us physicists, are friends in that they are very easily detected. Actually, perhaps if I just flick back to my picture of LHCb, where is it? Yeah, so LHCb is as plenty of material there. There's a layer after layer. If you look from right to left, right on the right hand side is where the interaction, the proton-proton collision occurs, and the LHCb detector is everything that's to the left of that across the screen. And all these layers, the purpose of all these layers is to track the passage of each one of the 30 to 50 particles that come out of the proton-proton collision every 25 nanoseconds. So this thing's a factory of just responding to the passage of a few dozen charged particles every 25 nanoseconds, 40 megahertz. Yeah. So it's quite a job for this detector and then the computing infrastructure behind it in order to detect these things. So you need to look for particular signatures for things you're very interested in. And the muons actually turn out to be very interesting. Because the muon is a lepton, it does not interact with the nuclear matter of material very easily. Okay, unlike a hadron, which does connect through the strong force to interact with the material of the detector. The muon doesn't. It's a lepton, so it punctures its way all the way through the detector from the right-hand side in the picture to the left-hand side. It punctures its way through. So our muon detectors, or what we call a muon filter, is at the very back of the detector. And if particles get that far and form a very nice track of hits in the detector, several hits one after another, which is what we call a track, then you can be pretty sure if it's got that far, if it's penetrated its way all the way through the rest of LHCb, that it is a muon. An electron also is a lepton, and so also doesn't interact with the detector material very well through the strong force. However, it is very light. The electron is very light. It's it is 200 times lighter than the muon, which means it's much more easily knocked around and scattered by the electrons in the matter, by the electric fields, the nuclear electric fields. And so the electrons scatter more easily, so they're much harder to reconstruct cleanly. But the muons zip right the way through the detector. You detect them in the muon filter and cleanly identify them. So everyone likes doing particle analysis involving muons, I can tell you.
Thanks, Malcolm. So there's a couple more questions. I noticed some people are leaving because we reached 1 o'clock. If it's okay with both speakers, I have 2 more questions and then we'll finish the talk. Is that okay?
Fine with me.
Great. Okay, so John had said there seems to be some difference from the standard model in other areas too. For example, in bottom quark decay, which does not produce the expected 50-50 electron-muon distribution. Is this connected in any way to the muon results? He then posted, it sounds like you were addressing it, so I'm not sure if John is happy with the answer, but if you think there's anything else to add, please do. Thank you.
I suspect he is.
Great, and so then another question, let me get here. From another John, is the media have perhaps predictably jumped to a new particle and or new fifth force? How misguided are they?
I don't personally think it's misguided. I understand that people want to seek explanations, and I think it's very exciting to do so. And I even indulged a bit in it myself, didn't I? But I think yes, as long as people are who are looking at this critically can put it in perspective, I think it's absolutely fine that people try to put exciting language around it.
That's brilliant. So thank you. It looks like we don't have any more questions. I'm going to give you half a second in case anybody has a last minute one. We're getting lovely comments on the chat box and thanking both speakers for a wonderful talk. And so I'll take this opportunity to thank Again, Sam and Malcolm, very much for your talk today, and to everyone who joined us. And to remind you, today's our last day for the physics booth at Meeting Minds. So we'll have a physics cafe at 4 o'clock. It's very informal. We have volunteers from around the different areas of research in the department. So you can just meet us for a very informal chat. And then at 5 o'clock, we're going to have a wonderful tour of the solar cell lab. It's the Henry Snaith lab with Alexander Ramadan. So I look forward to seeing many more of you later on. And again, thank you very much for joining us today. Goodbye. Thank you.